Hello, welcome to this lesson. Relative atomic mass. The masses of individual atoms are very small. Remember our cube? We could divide it so many times. It could be very difficult to weigh the mass of that cube by the time we reach maybe the millionth division. It is therefore very difficult for us weighing balance in the laboratory to measure the weight or the mass of a single atom. Through many experiments, scientists found out that the mass of an atom is in the range of 1 times 10 to the power of negative 22 grams. Very small. It is more convenient to express the mass of an atom relative to a chosen standard element. Initially, a hydrogen atom was chosen as a reference point since it was the lightest. For example, the relative atomic mass of sodium was said to be 23. That means sodium weighs 23 times more than hydrogen. However, this reference was not very convenient because in the 20th century, the hydrogen scale was criticized because of the existence of isotopes of hydrogen. Do you remember the isotopes of hydrogen? Again, scientists decided that they're going to refer to the oxygen atom as the reference point. It was known as the oxygen scale. This also led to different inconveniences because of the existence of isotopes of oxygen. And therefore, in 1961, the International Union of Pure and Applied Chemistry, usually abbreviated as the IUPAC, came up with a new scale based on the carbon-12 isotope. In this new scale, carbon-12, which you write as C12, contains 6 protons and 6 neutrons and weighs exactly 12 atomic mass units, which is also abbreviated as AMU. In this scale, it was convenient because we only referred to carbon-12 and not any other isotopes of carbon. And also, the isotope of carbon-12 weighs exactly 12.000 atomic mass units. This led to a new definition of the relative atomic mass as follows. The relative atomic mass of an element is the ratio of the average mass per atom of the naturally occurring form of the element to 1/12 of the mass of carbon-12 atom. Remember, the mass of carbon-12 atom is 12 atomic mass units. So if we are comparing with any other element, we have to take 1/12 times 12 atomic mass units to give us 1 atomic mass unit, and therefore this one can be used to compare any element. For example, when you're talking about nitrogen, the mass of nitrogen would be calculated as follows. You would say that nitrogen has 7 protons and 7 neutrons, giving us a mass number of 14. This mass number is compared to the mass of 1/12 times 12, which is equals to 1 atomic mass unit of carbon-12. Therefore, nitrogen is 14 times heavier than the mass of 1/12 of 1 atom of carbon-12. In the previous class, we concluded by saying that the relative atomic mass of nitrogen is 14, meaning it is 14 times heavier than the mass of 1/12 of carbon-12 atom. Scientists have also discovered that we have 2 isotopes of nitrogen. The first one is nitrogen 15 and the second is nitrogen 14. So you ask yourself, nitrogen 15 weighs 15 times more than 1/12 of carbon-12 atom, whereas nitrogen 14 weighs 14 times more than 1/12 of carbon-12 atom. So which one do we choose? Chemists have come up with a way of averaging the 2 masses so as to come up with one figure for nitrogen and all other elements that contain isotopes. Let us see how. Nitrogen 14 consists of about 99.634% of all the nitrogen in existence. Nitrogen 15, on the other hand, covers only 0.366%. So all nitrogen covers a total of 100%. Now for us to calculate the relative atomic mass of nitrogen, we need to carry out the following calculations. We need to take the mass of nitrogen 14 multiply by the percentage abundance, which is this here, divide by 100, and then we add the mass of nitrogen 15 multiplied by the percentage abundance divided by 100. So let us do that. The mass of nitrogen 14 is 14. Remember, this mass represents the mass number. So it is 14 multiplied by 99.634 divided by 100. And then we add 15, which is the mass number for nitrogen 15, multiplied by 0.366 divided by 100. When we calculate this, it would give us 14.00366. This figure is approximately 14.00, correct to 4 significant figures. And that is why we say that the relative atomic mass of nitrogen is 14. Let us carry on with a question. Neon exists in 3 isotopes, which is neon 20 with a percentage abundance of 90.5%. Neon 21 with a percentage abundance of 0.3%, and neon 22 with a percentage abundance of 9.2%. We need to calculate the relative atomic mass of neon. Remember our formula: relative atomic mass is equals to the mass of the first isotope, you can call it isotope A, times the percentage abundance divided by 100 plus the mass of isotope B times the percentage abundance divided by 100, and so on and so forth. This could go on until we cover all the isotopes. So for neon, we have 3 isotopes, and therefore the relative atomic mass will be equal to first isotope has a mass of 20 and a percentage of 90.5. So we have 20 times 90.5 divided by 100. Then we add the second one, which is 21 times 0.3 divided by 100 for the third isotope, which is mass 22 and percent 9.2 divided by 100. This one would be 18.1 plus 0.063 plus 2.09. When we add this, we find that the relative atomic mass of neon is 20.253. When you look at your periodic table, you will see that the relative atomic mass of neon is given as 20.253, or sometimes it could be rounded off to 4 significant figures and given as 20.25. Another example to help us calculate the relative atomic mass. Chlorine has 2 isotopes, chlorine 35 with a fractional abundance of 3/4 and chlorine 37 with a fractional abundance of 1/4. Calculate the relative atomic mass of chlorine. Remember, the relative atomic mass is equal to the mass of isotope A multiplied by the percentage abundance divided by 100 plus the mass of isotope B times percentage abundance over 100, and so on and so forth. However, we have been given the fractional abundance. In this case, the first step is to convert the fractional abundance into percentage abundance. So, for chlorine 35, we are going to calculate as follows. Three quarters multiplied by 100 to give us 75%. For chlorine 37, it is 1/4 times 100 to give us 25%. Therefore, now we can easily calculate the relative atomic mass as follows. Chlorine 35 has a mass of 35, multiply by 75, divide by 100. Then we add chlorine 37 multiplied by 25 over 100. This would give us a mass of 35.5, and therefore the relative atomic mass of chlorine is 35.5. You can also look at the periodic table and confirm this. In this example, we are going to hide the identity of the element. So the question goes, an element Y has 3 isotopes with mass numbers 40, 39, and 41 that have percentage abundances of 0.01%, 93.1%, 6.89% respectively. Determine the relative atomic mass of element Y. As usual, you remember the formula. Relative atomic mass is equals to the mass of the first isotope A times the percentage abundance divided by 100 plus the mass of isotope B times the percentage abundance all over 100, and so on and so forth until we cover all the isotopes. So in this question, we shall have the relative atomic mass as the first mass and the first percentage. So it is 40 times 0.01 divided by 100. Then we add 39 multiplied by 93.1 divided by 100, and then we add 6.89 multiplied by 41 divided by 100. This gives us 0.004 plus 36.309 plus 2.8249. When we add all this, we get 39.1379. On average, we could say it is 39.14, correct to 4 significant figures. Pretty easy, right? Yes. Can you check the periodic table and try to search for the element with relative atomic mass of 39.14 or closer